There we go. All right, so today we're going to learn how to perform a multiple linear regression analysis in SPSS. Our focus is going to be on evaluating the fit of the model via assumption checking and through diagnostic measures, and also learning how to run a hypothesis test about the parameters of the model. So this is the material that we will need for lab assignment number 5. And to demonstrate this material, we're going to use the Fuel.sav dataset. So the Fuel.sav dataset should be available on Blackboard. I'm just going to double check that I dropped it in there. Lab data. Yeah, there it is, Fuel.sav. So as per usual, we're just going to upload this onto our onto the server. All right. Okay, so there we go. Right, and then we're going to open this. And we can take a look at it. Okay. All right, so we don't need this stuff for now. We can just focus on what's given here. So you can see in this data set, we have 3 different measurements. We have fuel C, which is the fuel consumption of these cars. We have the temperature, which is the temperature of, let me see if I have the background, is the outdoor temperature. I assume this is in degrees Celsius, it would look like. And then we have the wind velocity outdoors. So we have fuel consumption of a car, the temperature outdoors, and the wind velocity outdoors. What we want to do is build a linear model that relates the fuel consumption to the temperature and the wind. So in part B, we're going to propose that model. But before we do that, we're going to study the correlation between the values in the data set. So in part A, it says find the correlation coefficient between all pairs of variables, comment on the relationship. So to do this, we go analyze, correlate bivariate, I believe. Yep, analyze, correlate, bivariate. So let me just show that path again. Correlate, bivariate. All right. And then we add all 3 values into the variable section, and we make sure that Pearson is checked. The significance part isn't really of interest to us. We can get a hypothesis test for the correlation values, which can tell us if it's a significant correlation. But for the purposes of what we're doing, we're just going to report the values and then give the interpret said values. All right, so we'll click OK, and then you can see that the correlations are reported in this table below. Okay, so we're going to take this table here, and we're going to insert it here. All right. So we have the following. The correlation between fuel consumption and temperature is negative 0.879. The correlation between fuel consumption and wind velocity is 0.424. The correlation between temperature and wind velocity is negative 0.71. Okay. So this implies the following. the correlation coefficients indicate that there is a strong negative linear correlation between fuel consumption and temperature. So the value negative 0.879 indicates that we have a relationship that is negative. So as one variable increases, the other one decreases. And it's a strong relationship because the value is negative 0.879, which is quite close to negative 0.9, which is quite close to 1 or to negative 1. So this would indicate a strong linear relationship. Thank you, Nick. Okay. The correlation coefficient. Okay, so the correlation strong. They also indicate that there is a mild positive. Even mild might be a bit of a stretch here. So between fuel consumption and wind velocity, we have a relationship of about 0.424. That's not very strong. So I'm gonna write this actually as weak because it's less than 0.5. So it indicates that there is some trend. So as one increases, the other increases as well. So fuel consumption and wind velocity do appear to be increasing together, but it's not a strong relationship. So there's some trend. I would call it a weak positive linear trend in this case because it's less than 0.5. We'll get a better illustration of this momentarily when we go to evaluate the assumptions. Temperature. Finally, that there is effectively no linear relationship between temperature and wind velocity. Okay, so we have the correlation coefficients indicate that there's a strong negative linear correlation between fuel consumption and temperature. They also indicate that there is a weak positive linear relationship between fuel consumption and temperature, between fuel consumption and wind velocity. Finally, finally, the values indicate there is effectively no linear relationship between temperature and wind velocity. So that value is negative 0.071, which is very close to 0. A value very close to 0 effectively means there's no linear relationship, or there's no evidence of a linear relationship in this case. So we would say that there's effectively no relationship between temperature and wind velocity. And this is ideal because we would want, as we are going to see, there to be evidence of a linear relationship between fuel consumption and temperature and between fuel consumption and wind velocity, because we are going to try and predict the fuel consumption from these two variables. But we don't want temperature and wind velocity, which are the explanatory values, to be linked in this study. Okay, so in part B, we want to propose an MLR model to relate fuel consumption to wind velocity. Okay, so we're going to have the following. Insert equation. All right, so we're going to have here beta, y. And then we're going to have to subscript this thing. I is equal to beta zero plus beta 1 x1 I plus beta 2 x2I plus plus epsilon I. Comma. All right, and oh, sorry. Where? Okay, where in this case x1 is the represents the wind velocity. Actually, this will be representing the temperature, I believe. And x subscript 2I represents the wind velocity. Okay, and then the yi represents the fuel consumption. All right, and then all other terms would be as defined in the lecture notes. So beta 0 will be the theoretical y-intercept. Beta 1 will be the slope representing the a unit increase in the temperature as it relates to fuel consumption. Beta 2 would be the slope representing a unit increase in wind velocity as it relates to fuel consumption. And the epsilon I will be the normally distributed errors that we use to evaluate the model. Okay, now in part C, we want to evaluate the assumptions of the model. Okay, so there are 4 assumptions when we fit an MLR model. They are the same 4 assumptions that we talked about last week for the SLR model. So the first assumption is that there is a linear relationship between the response variable and the explanatory variables. All observations are independent and collected via a simple random sample. The response variable is normally distributed. The response variable has constant variance. Okay, so to evaluate the 4 assumptions, we'll start with assumption 2 because this just requires knowledge of the experiment. So, is the amount of fuel required to heat a home depends on the outdoor temperature and wind velocity. Okay, so we'll just assume that this is true based off what's given in the course outline or given in the lab manual. So assume true based off description given in lab manual. So the SRS assumption, like we've talked about before, I mean, the only real way to evaluate it is to understand like where the data came from. So in this case, we don't have a lot of background information outside of a description of the variables. It just says they used a sample of 10 winter days. So we'll assume that this sample can be considered an SRS for the purpose of the problem. All right, in part 1, we want to investigate the linear relationship between the response and the explanatory variable. Now, we've actually already done part of this because we've constructed the correlation values above. So we know from our correlation analysis that there is evidence of a strong negative linear relationship between fuel consumption and temperature, which is what we would like to see. There's no relationship between temperature and wind velocity, which we also want to see. We don't want the 2 explanatory values to have any relationship. And there's also evidence of a relationship between fuel consumption and wind velocity, which again, we would like to see because we're trying to relate fuel consumption to wind velocity. So to visually inspect this, we can use a pairwise scatter plot. So to construct the pairwise scatter plots, we would go graphs, legacy dialogues, scatter/dot. Then we would choose matrix scatter. So graph, legacy dialogues, scatter/dot, matrix scatter. Click define. Okay, now we're going to put all three variables inside the matrix variable category. Titles. So here we'll have pairwise plot of fuel consumption, temperature, and wind velocity. Click continue, click OK. Okay, and here's our pairwise scatter plot. So from the scatter plot, we can actually see evidence of what the correlation coefficients were indicating in part 1A. So we can take this, we can insert this here. Let's see if I can just... Okay, so the scatter plot here is giving us effectively the same evidence that the correlation coefficients are giving us, but now we can evaluate it from a visual point of view. So you can see that when we compare, so the way we read the scatter plot again is if we go down this axis, this is telling us the y-axis of each grid. And if we go across the x-axis, this is telling us the x variable for each grid. So this plot here is showing us fuel consumption versus temperature. And you can see that this appears to be linearly, these two variables appear to be linearly related. So as temperature increases, fuel consumption decreases, right? And you can see that these points, again, appear to fall on a straight line and they're quite tight to one another. So, and we know that the correlation coefficient here is negative 0.879. So this would certainly give evidence that fuel consumption and temperature are linearly correlated, which is what we would like to see. If we compare fuel consumption to wind velocity, you can see here that there's evidence of an increasing trend. So as wind goes up, fuel consumption goes up. But we have some points, these 2 points in particular, that kind of deviate from the linear pattern. So that's going to cause the line to kind of get pulled away from this region here and sort of go more through the middle part there. And that is why we see the lower correlation coefficient of 0.424. If we look at temperature versus wind velocity, just for illustration, we can see that this appears to be a fairly random plot. And that's why the correlate is really due to these points here, actually, why that correlation is so close to 0 for this particular scatter plot. But we're only really interested in these two for evaluating the linear assumption. So here we can say, based the pairwise plot shows, reinforces what was insinuated via the correlation analysis. That is, we can see that fuel consumption has a linear relationship with both the temperature and the wind velocity. Therefore, we can assume that assumption 1 is intact. Any questions so far? Okay, so for assumption 3 and assumption 4, we're going to use a residual analysis. And this will be identical to what we did in the last lecture set. So we're going to compute the residuals, and then we'll construct a QQ plot of the residuals to check normality. And then we will plot the residuals versus the predicted values to check constant variance. So to do this, we're actually going to have to run the full regression procedure anyway. So we're going to get our output for the next few questions from this part. So to run the regression model, we go analyze, regression, linear. So for the MLR model, we have analyze, regression, linear. Our dependent variable is fuel consumption. Our independent variables are both temperature and wind. And then to get the residuals, we would click save, and then we would go unstandardized predicted values, standardized residuals. So this is pretty much the same process that we've used when computing the residuals in the past. So again, we find this through the save feature, unstandardized predicted, standardized residuals. Okay. Under statistics, we make sure estimates is clicked, model fit. We can also take the confidence intervals if we want. Continue, click OK. All right, so you can see that there's a variety of output here. We're going to use this output in the next few questions to evaluate the fit of the model. So we're going to need the coefficient part here and the model summary part here. But for now, we're going to use the predicted values and the standardized residuals to, again, test those model assumptions. So starting with normality, we're going to create a QQ plot of the standardized residuals. So analyze, descriptives, QQ plot, standardized residuals against the normal, click OK. And that gives us the following. Right, so we'll just take this plot here. And then we'll insert that here. All right, and then we can see here the residual values appear to follow or appear to form a straight line relationship with the quantiles of the normal distribution. Therefore, the data give no evidence to suggest that the variable of interest is not normally distributed, that the response variable is not normally distributed, right? So that's a pretty standard interpretation. I mean, we've seen a lot of examples of evaluating QQ plots throughout the course. Our rationale for using those is exactly the same, just looking for a straight line relationship with the quantiles of the normal distribution. Okay, for the response variable, or for the constant variance assumption, we're going to create a scatter plot of the residuals versus the predicted value. So we have graph, legacy dialog, scatter / dot. This time we're going to use a simple scatter plot. On the y-axis, we'll put the residuals, and on the x-axis, we'll put the standardized values. So here we're going to have residual versus fitted values plot. We'll just say residuals versus fitted values. Click continue, click OK. Okay, and then here's our plot of the residuals versus the fitted values. And then all we're looking for here is randomness. So we just want it to look like there's no relationship between the values. Okay, so in looking at this plot, we can say the residuals versus fitted value plot shows that appear to be randomly scattered with no obvious trend. Therefore, this plot is no evidence to suggest that the variance is of the response variable is not constant. And we saw an example of this type of analysis last week as well. So for both the MLR model and the SLR model, the way that we go about evaluating the assumptions is actually exactly the same. The only difference in this with this material is that we're including an extra explanatory variable. So instead of having y equals b0 plus b1x, we now have y equals b0 plus b1x plus b2x. But in terms of the normality and the constant variance assumption, we have the same approach for both, for evaluating both of those. All right, in part D, we want to fit an MLR model to the data. So we did that already. When we clicked Analyze Regression Linear, following that process actually outputs what we need for the regression analysis. So if we scroll up a little bit, we can see that the values we need for fitting the model are given in the coefficients table here. So we can take this table here, insert that below. All right. So now what we would have is, just taking this from above. Right, so we're going to have y equals 11.928 plus negative 0.628 plus 0.130. Okay, and then the yi here is now an estimate based off the regression line, so we need to put a hat on top of this. So accent hat. All right, so that's our fitted regression line based off the output. Okay, so we can say a few things here. We can write if the, so this would be for interpretation of beta 0. Okay, so if the outside temperature and wind velocity are both equal to 0, then we expect a home to consume 11.928 units of fuel. Okay. For beta 1 and beta 2, we would have, for beta 1, we would have if wind velocity is held constant, then we would expect a home to consume negative 0.628 well, it's better. Okay, so if wind velocity is held constant, then for every unit increase in outside temperature, we expect a home to consume negative 0.628 units of fuel. And then for beta 2, we would have, if the outside temperature is held constant, then for every unit increase in wind velocity, we expect a home to consume 0.130 units of fuel. So in this case, we're basically just interpreting the slopes in the context of the problem. But because it's a multiple linear regression problem, the interpretation of each slope only works if the other value is held constant. So for beta 1, we're talking about the relationship between outside temperature and fuel consumption. So for beta 1, we have to hold wind velocity fixed, and then we can discuss the increase in outside temperature, or then we can discuss the change in the amount of fuel used with every unit increase in outside temperature. For beta 2, we're talking about the relationship between wind velocity and fuel consumption. So in this case, we would say for every unit increase in wind velocity, we would expect the home to consume 0.13 units of fuel if we fix the outside temperature to be constant. All right. In part E, we want to calculate the adjusted R squared and interpret the value. Okay, so the adjusted R squared is given here in model summary. Okay, and then again, that's part of the regression output. Okay, so we would have adjusted R squared equals 0.877. And then we can say the fitted regression line accounts for 87.7% of the variation in the response variable. Okay, so this is just the standard interpretation of the adjusted R squared value, basically just saying the line accounts for 87.7% of the variation in the, actually it would be in the fuel consumption of the homes, which is quite high. All right, and then finally, in part F, we're asked, does the data give evidence that fuel consumption decreases as the temperature increases, evaluated at the 5% significance level? Okay, so for this, the assumptions were all checked off in part E, or part C. So our hypothesis tests are going to use the same assumptions from model C. So for the assumptions, we can write C, C. And now the hypothesis test will take part in the usual 6 steps. So we want to test H0 that the fuel consumption decreases with respect to outside temperature. So we're going to have our outside temperature is represented by beta 1. So if fuel consumption decreases, we would expect beta 1 to be less than 0. So we're going to have HA beta 1 equals 0 versus, or sorry, we're going to have H0 beta 1 equals 0 versus HA beta 1 less than 0. We're testing at the 5% significance level. So we have alpha equals 0.05. Our test statistic is going to come from the same output that we used to fit the regression model. So we can insert the same table here. All right, so T equals, for temperature, negative 0.7275. Sorry, negative 7.275. Okay, on step 4, it's a one-sided test, so the p-value will be equal to 0.000 over 2, which is 0.000. So on step 5, we can reject H0 0. And then on step 6, we can conclude at the 5% significance level, the data provides sufficient evidence to suggest that the fuel consumption of each home in this population decreases with each unit increase in outside temperature. All right. Okay, and there you have it. MLR analysis via SPSS. So this is the material that we need for lab assignment number 5 for part B, or question 2 on lab assignment number 5. So lab assignment number 5 is currently scheduled for Monday. I'm just going to extend that to Wednesday again to make it consistent with the last one. And because it's the last lab assignment, so it's not, I think it's okay just to give it a few extra days since we just got to the MLR material today. And so lab assignment number 5 focuses on lab session 9 and lab session 10. So basically lab session 9 relates to question 1, lab session 10 relates to question number 2. And in each of those cases, we're using an SLR model and an MLR model respectively. Do you guys have any questions for me? Yeah, so I was going to finish off with a note about that today, and then I was going to send out more details via email. So next week, we do not have a lab session because it's Easter holiday, but the week after, we will return with the lab exam. So the lab exam will take place during the Friday lab session. It will be held via CrowdMark. So I imagine most of you have had quizzes over CrowdMark through either my lecture class or the other lecture class. So that'll be run in the same way. You'll be sent the questions via the CrowdMark page. You'll be sent the data sets and whatnot, and then it'll just be a matter of completing the questions within the 2-hour lab time frame. Any other questions? Yeah, the lab final is a cumulative exam. On that note, we will have more details next week. So John and I are going to meet on Tuesday to discuss the setup of the final and get their practice materials ready. So there will be, like practice exams essentially that you can use to get prepared for the test. Any other questions? Okay, so if there's no other questions, then I'll stop at the teaching portion for today. As always, I'll be here for the remainder of the session in case you have any questions. But if not, I will send out more detail regarding the lab final in the next week, regarding the last lab assignment. And I guess the next time I'll talk to you guys will be the final Friday of the semester, which I believe is April 9th. And that's when we will have the lab exam.